Vectors are a different way to look at measurement. Here at the top I've made a note that vectors deal with both magnitude and direction. As a little aside, numbers we've dealt with in the past would be referred to as scalar values. These are values with no direction. So I should make a note of that. So this would be something like if I told you that a car was traveling at 30 miles per hour. If I just said 30 miles per hour, so some car is just traveling at 30 miles per hour. So we'll just call that an example. This would be a scalar value because I don't know where the car is going. If I tell you that the car is moving at 30 miles per hour north, then I've given you a very specific kind of scenario. So a scalar value might be this, and then direction is obviously where something is headed. You need both of these things in order to create a vector. So we'll just go with the example I just mentioned of going north. So if I said that something was going 30 miles per hour and heading north, we could put those together. We could say 30 miles per hour and north, and this right here would be a vector quantity. The idea being that I know how fast I'm going, and I know where I'm going. In general, vectors aren't necessarily all that complicated in the sense that they really are just putting two things together. It's just a fancy word for saying, look, we know how much and where. And we can even represent this visually with an arrow pointing in the direction that we're headed with that particular magnitude. So if I made this 30 and said we're heading north, so maybe I'll go in and just put this little right here. This ray right here, this arrow that I've drawn, would represent 30 magnitude heading north. That's going to be the basic idea behind vectors, is just setting up a magnitude and direction and being able to break them down in some way. And so what we're going to be working with, or expected to be able to work with, is let's say we were given a vector that points in this direction. Let's call this vector v, so we use a little v hat here. We're going to be expected to be able to break this thing down into components, or maybe even build it back up from components. We're going to see that every vector has some sort of horizontal and vertical component to it. Now I've drawn one here that's going to have a positive horizontal and a positive vertical component. I should point out now that there will be negative variance as well if it's pointed in certain directions. In fact, if you're used to working with quadrants, that's how we're going to talk about this in future videos. The idea is that you create a little right triangle here, and our direction is typically measured in this direction here from the positive x-axis. Theta is almost always measured from the positive x-axis and counterclockwise. I'll make that note here. It's really important to note that because if they give you no other directionality or no other way to talk about it, so for example here, instead of saying 90 degrees, I said north. So notice that the idea being that if I go from the positive x-axis and I head in this direction, that would be a 90-degree angle. So I could have said 30 miles per hour, 90 degrees, but instead they said north. So in general, we're going to use this, but there are alternate ways to talk about angles, and we'll probably see that in future videos. But we can use some basic right triangle trigonometry, we can use the Pythagorean theorem to relate everything that we're going to talk about down the road. We would call our horizontal component the vector v sub x, and we'll have v sub y for our vertical component. And the idea being that we're thinking of this in terms of coordinate plane often, so x direction, y direction makes sense. There are going to be four basic formulas that we'll tend to for the most part. We want to know that with a right triangle, the legs squared and added together equal the hypotenuse squared. So if we're trying to find the magnitude of the vector and we know what the components are, then we could take the magnitudes of those components and just use the Pythagorean theorem. And they often use some kind of double bracket bars here, or they'll use single bars to show magnitude. But we'll put a little square there as well. And notice here I don't use the bars for Vx and Vy. The main reason for that is that Vx is already telling me mostly directionality. If I know it's a negative Vx value, then it's heading left or west, and if it's positive, it's heading to the right, to the east. If this is positive, it's heading north, or negative, it's heading south. So Vx and Vy actually have their direction built into the numbers, whereas the magnitude of V itself will always be positive because it's the hypotenuse, just like we've seen in the past. All right, the next thing we would want would be to find theta. Well, theta is related to the components. They're opposite and adjacent sides, so we could take tangent inverse of our opposite over our adjacent, and that would actually work out pretty well. Now, both of these formulas assume that we have our components, so we're provided with components to get there. But if we don't have our components, if instead we're working in the other direction, if they give us the magnitude and the angle, the magnitude and the direction, we could find Vx pretty simply. We could take the magnitude of our vector and multiply by cosine of our angle. And that should be pretty obvious in a way, because our angle here is related to the adjacent and the hypotenuse by cosine. So cosine of theta would be adjacent divided by hypotenuse, but we would want to multiply both sides by that hypotenuse to get this by itself. And in the same fashion, if you can get to that part, then this should be pretty much obvious. If we're going to work the opposite side instead, we'll just use sine of theta. So these four formulas are going to be the bread and butter of this entire discussion on vectors. We're going to be able to come back to these pretty frequently. Our first skills that we'll look at will just be if you have the components, be able to find your magnitudes, or if you have initial points and endpoints. If they came up here, if they define somewhere in space that they've placed this vector, you could use this initial point and this terminal point to actually identify the magnitude of this thing, because you'll be able to figure out how wide and how tall this right triangle you could draw would be. And so that's good notation to make a note of as well. These would be initial and terminal points where the arrow always points in the terminal direction. But otherwise, I'll break this down skill by skill as the videos move forward. So if you have questions about any specific skill, see if there's a video about that first, and then just reach out to me if you have questions.